Hey guys, this is a short presentation on the project we carried out for IE555. We've tried to incorporate workflow interference in facility layout design using Python programming. So let's just jump right in. So in a traditional facility layout problem, the amount of workflow between facilities and the distance is usually considered. In this case, you have I, J, K, L, M, and N, which are facilities. So as you can see from J to I, the amount of material that's flowing is 35 units. And if you want to reduce the amount of material handling effort, you normally reduce the distance. And the amount of congestion between the routes is not something that's considered. So in the workflow interference model that we've tried to implement, so in this case, you have two AGVs at two different facilities, I and J. So from I to J, the AGV is moving with 20 units, and from J to I, it's moving with 12 units. So obviously the AGV at facility J is going to have to wait till the AGV at facility I comes back to J. So there's really a conflict. And why are conflicts of interest? They basically delay production, and it's going to cost you a lot of money. The reason why this problem is important is because factory space is something that's important. You know, aisles are narrow, AGVs are wide, and it makes no sense to accommodate two AGVs in a single aisle by expanding the aisle. That's just going to cost a lot of money. So one workaround to this is by incorporating workflow interference by assigning workstations to locations in such a way that it reduces congestion. And this, of course, is not something that's considered in a traditional facility layout problem. So this is just a sample layout for 7 facilities and locations. 1, 2, 3, 4, 5, 6, 7. These are all locations. And our code is going to come up with the optimal assignment of these facilities I, J, K, L to these locations such that it reduces the congestion overall on the factory floor. So this flowchart represents the heuristic that is going to be implemented in our Python code. So the basic idea is that some partial assignments are done for facilities and locations, and constraints are checked. So these constraints are called upper bounds and lower bounds. So upper bound is basically any feasible solution, and the lower bound is basically something that I'm going to get to in a moment, but it refers to the sum of all interferences of conflict points. Again, something that's going to be discussed in the subsequent slides. But the idea is that whenever the upper bound goes below the lower bound, we know that the assignment is going to be incorrect, and we fathom that assignment, and it goes back to the top. And this process sort of just iteratively proceeds till all assignments have been made, after which the algorithm stops. So there are different types of conflict routes. So 1, 2, 3, 4, 5, 6, 7, like I said, are all the locations. Now in 1 and 2, you have, let's say, facility I is assigned to location 1 and facility J, which is assigned to location 2. In this case, there's going to be a direct conflict. It's the example of the AGV example we discussed earlier. And 2 and 4 and 4 and 2. This is going to make sense when I bring out the next slide. Yeah. So in this case, this makes more sense because I'm going to explain it from here. So 2 and 4, 4 and 2. Now, like I said, J has been assigned to location 2. So 2 and 4, the amount of interference that's going to be happening is something that we check from this side. So 2 and 4 is going to be somewhere from here, which is 14. 14 is the minimum amount. And from K, it is to J, right? So it's 7. So minimum of 7 and 14 is taken to be 7. And this is how the interference is calculated. Now, if you see for 1 and 3, 3 and 1, I is assigned to location 1. So from I, which is the minimum amount of material handling effort, is at 13 units at K. We're using K again and again because K is not something that's been assigned just yet. that is something that will be happening later down the process after the lower bound has been accepted below the upper bound. So in this case, for 1 and 3, 3 and 1, it's going to be 13 units from I to K, and from K to I it's going to be 2. So minimum of that is taken to be 2. And the sum of all these conflict points, the sum of all these interferences is calculated to be the lower bound. And the upper bound is going to be any feasible solution. And the feasible solution is going to give us a list of facilities that are going to be assignments to these corresponding locations. So I'm just going to jump right into the code that we used to solve this problem. We have a couple of big functions that do most of our tasks. Calculate essentially calculates the constraints, and it churns out viable routes based on the constraints that were discussed here. And compress matrix basically manipulates the cost matrix here. This is going to be our input for 7 facilities and locations. And let's just run the code. All right. So the final feasible solution is at 26,536. This is going to be the cost of assigning these facilities to these locations. And this is going to be the final layout. As you can see, the yellow markers are depicting the movement of material from across different facilities. Like I said, I to J, J to I, there's a direct conflict. And in this case, J to M and I to N, there's indirect conflict, which means there's some sort of potential interference that we'd like to avoid in an ideal situation, which is why this whole process of calculating lower bounds and upper bounds really helps, because it helps you come up with the optimal facility layout. And yeah, that's it. If you have any questions, please feel free to drop comments below the video. Thanks for watching.